Hi, Physics 2. Mr. Janowski here. This is the third part of the Chapter 36 slides. So in the first part, we learned some of the history of magnetism and the basics of magnetism. In the next part, we learned that current flowing through a wire that's in a magnetic field can cause there to be a force upon that wire. And today we're going to learn something that goes along with this, and we're going to get a little bit more sophisticated with it too at the same time. So let's get started with that. So that first day, what was the first right-hand rule that we learned? We learned Ampere's right-hand grip rule. So if you've got current flowing through a wire, grab that imaginary wire with your right hand, such that your thumb is pointing in the direction of the current, and that moving current is going to create a magnetic field around that wire in the direction that your fingers wrap around your fist. So that was what we learned in the first part of the slides. What was the second right-hand rule, which should be a hyphenate? I skipped it. Oh well, I'll fix it later. The second right-hand rule is what I'm calling the cross-product right-hand rule. So if you've got a moving charge, a moving positive charge that is, hold out your right hand so that your thumb is in the direction of the moving positive charge. Your fingers are in the direction of the magnetic field, and then your palm will be in the direction of the force that is felt by that moving charge, or if it's a current going through a wire, on the wire. So what is the formula for the force on a current carrying wire in a magnetic field? That formula is, here's two versions of it. The vector version, which we're not really going to deal with too much, but it's F is equal to I L cross B, using the cross product there, the vector product. We'll mostly deal with this one. F is equal to I L B sine theta. So this helps us get around doing the vector math. In this version that we're going to do, theta represents the angle from L to B. So we're not going to even worry about the sign of that angle. Sign is in positive or negative, not sign is in the trig function sign. We're not going to worry about if it's positive or negative, because we're going to keep using the right-hand rule to figure out the direction. So we'll just make all of these, I, L, B, and theta, all positive numbers, and then the right-hand rule will tell us what the direction should be. Whereas if you do it the rigorous way, using the vector math correctly, that will tell you the sign directly, but I don't feel like teaching you vector math, and you don't want to know it from me. So if we're looking at this, which way is this magnetic field pointing? Am I looking at tail feathers, or am I looking at arrow points? I'm looking at arrow points. So this is a magnetic field that's coming towards us out of the page. So now we're going to have an electron entering this magnetic field, traveling with some velocity v to the right. So which way will this electron deflect once it enters the magnetic field? So think about the way think about your second right-hand rule and apply it and figure out which way the force is going to be. And the force is going to be up. Now you may be holding your right hand in front of your face with your thumb pointing to the right and your fingers pointing towards you because the magnetic field is pointing towards you, and you will notice that your palm is pointing down. However, the force that this electron will feel is up because electrons have a negative charge. So there's two ways of dealing with the situation, and I'm going to suggest you just pick the one that works, whichever way makes the most sense to you. You can either only use your right-hand rule, always do right-hand rules, and then just flip your answer at the end when you're dealing with a negative charge or a negative current, or you could do the same thing with your left hand. So first try with your right hand. Hold your hand in front of your face, point your thumb to the right, point your fingers towards you, and notice your palm is pointing down. So that's saying the force should be going down, but oh wait, it's an electron. Those are negatively charged, so I've got to flip it. The force would actually be going up. The other thing you can do is hold your left hand in front of you. Hold your left thumb to the right. Hold your fingers pointing towards you, so you're going to be bending your hand back towards you in kind of an uncomfortable way, and now your palm is pointing up. So whichever way works for you, either do right-hand rules always and flip it when you have a negative charge, or use right-hand rules for positive charge and left-hand rules for negative charge. Whichever works for you, it's up to you. So to illustrate that point, pretend you have an imaginary wire in front of you and that there is conventional current going upwards through that wire. So we're going to try to figure out which way is the magnetic field created by this current. You can grab that wire with your right hand and notice which way your fingers curl, and you're going to see that the current's going like this. Now, the other thing you can do is same wire, the current's going the same direction, but this time grab it with your left hand and point your thumb down, because you're not interested in the current this time. This time you're interested in the negative current. You're interested in the way the electrons are actually flowing. If you do it like that, it's going to be hard to hold your hand this way. But you should notice that your fingers are actually curling in the same direction as they were in the top example. So either way you do this, you should get the magnetic field. So either right hand rule or left hand rule, just figure it out. So back to our electron entering this magnetic field. So the electron's going to the right, the field is coming towards us. This is going to feel a force up, and it's according to this formula. Focus on the bottom one. F is equal to QVB sine theta. So it looks a lot like the other one. The other one was ILB sine theta. This is QVB sine theta. Where Q is your charge, V is your velocity, B is your magnetic field, and theta is the angle from V to B. So yeah, very similar to the other formula we learned in the previous part. So think of this for a second. So this electron's coming in here, the electron's going to the right, it feels this force up. What path is this electron actually going to follow as this happens? It's going to follow a circular path, because if we look back, look at this picture compared to this picture, notice that the force is always perpendicular to the direction of travel. Well, this is a centripetal force, so it's going to cause this electron to follow a circular path. So I actually did this when I was not at UVA back in the day, but when I was in Westchester. This is kind of a classic experiment that undergraduate physics majors will do for determining the charge to mass ratio of an electron. So I used a device, it may have been this exact one, it certainly looked very similar, where these two big loops here, these big black loops here, these guys has a pair in this particular arrangement. They're called a Helmholtz coil. So we've got, these are, that you can't see it because they're inside a case, but there's wires looped around many, many times here, going like this. So each of these loops has a radius r, and the loops are separated by a distance r. So yeah, r is the radius of each of these circles, and r is the distance between these two circles. And it just turns out that if you arrange your loops like this, and the current's going through both loops in the same direction, you get a fairly consistent magnetic field, almost a uniform magnetic field of even strength and even direction all the way through these guys. So look at this guy, right-hand rule. If your current's going this way, actually the current should be going the other way. Okay. Wait, now I'm confused. The current's going that way. Yep, the current should be going the other way. Okay, I think this arrow is actually wrong. If your current is going counterclockwise through these loops, you would have a magnetic field coming out of the page. So anyhow, the point of this is you've got basically a little electron gun right here. You're going to shoot out these electrons with a known velocity. They're going to, well, I should explain this part first. So yeah, we just got this formula for the force on a moving charge in a magnetic field. F equals QVB sine theta. So back to here. That force is a centripetal force. So remember Newton's second law, F equals ma. That means, this magnetic force is equal to mass times centripetal acceleration. Well, your formula for centripetal acceleration is v squared over r. So your right side is mv squared over r. QVB sine theta, theta in this case is 90 degrees, sine of 90 is 1. So this is just QVB. So you get this formula, you do a little bit of algebra, and then you can get an expression for Q over m, which is the charge of an electron divided by the mass of the electron, will be equal to that velocity times the strength of the magnetic field divided by the radius. So yeah, again, when you're doing this experiment, this is actually a little electron gun down here, and it shoots the electrons out this way, and you will know the velocity by knowing the voltage you're putting them through. You will know the strength of the magnetic field because there's a way to find the magnetic field created by Helmholtz coils like this. And you'll measure the radius using the little magnifier. I'm sorry, the little ruler in the back here. So the electrons come through here. They leave the gun. They're now in a magnetic field, so they've got a force going up as they leave, and so they move in this circular path. So the blue is not actually the electrons. There's a gas in here. As the electrons hit the gas, they excite it. As the excited gas molecules de-excite, they emit an electron, so you can see the little blue light. So yeah, anyhow, a neat little experiment. It's neat to see actual, the path of actual electrons going. Kind of neat. Major in physics, you'll get to do this. So we have a formula. Now let's do the math. So we've got an electron, which we know the mass of an electron, we know the charge of an electron. It's traveling to the right with this velocity. So about a tenth the speed of light. It's going 2.25 times 10 to the 7th meters per second. It's going to enter a 2.50 millitesla magnetic field pointing out of the page. So what force, magnitude, and direction will the electron feel? Here's your formula. And this electron's velocity is perpendicular to the magnetic field, so your angle is going to be 90 degrees. So you plug in your things, and you'll end up with this wee tiny force. Force is equal to 9.01 times 10 to the minus 15 newtons. It's a tiny force, but remember, electrons have very tiny masses, so it will cause a meaningful acceleration. So you have this. And then how do you figure out the direction? Again, you can either use the right-hand rule and then flip it because it's a negative charge, or you can just hold out your left hand and use the left-hand rule. So now we have the force and the direction. So the next part, how do we figure out what its radius of curvature will be? Well, F equals ma. This is a very one with everything kind of idea. Force equals mass times acceleration, Newton's second law. So your centripetal force is equal to mass times centripetal acceleration. So do the stuff, do the algebra, you get an expression for r, you plug in the things, including F, which we just found, and you'll get a radius of 0.0512 meters, or 5.12 centimeters. So this is for an electron traveling to the right, entering a magnetic field that is coming out of the page. How would this be different if you had a similar electron? Well, same exact mass, same exact charge, but this time it's traveling out of the page. So this one's not moving to the right. This one's coming towards us and entering this magnetic field, which is also coming towards us. So how can we figure out the force that this electron will feel, and how will it curve? Well, same formula, only this time the angle you're dealing with, theta, is 0 degrees, because the angle between the velocity of the electron and the magnetic field that it's entering, well, both of those are in the same direction, so the angle between them is 0. So sine of 0 is 0, so you're going to end up with a force of 0 newtons. So this electron, you can see in this handy graphic up here, this one's just coming this way in exactly the same direction as the magnetic field. So it's not going to put any force in it. This electron would just go straight through the magnetic field. So now, what would happen if we combined both motions at the same time? So instead of having an electron that's coming in through the right, or one that's coming in from the back of the page, out of the page towards us, what if this one were coming at some angle? So I've given you a new velocity, 2.574 times 10 to the 7th meters per second. And this is at an angle of 60.9 degrees to the x-axis in the xy plane. So it's not coming straight towards us like this. This one's actually coming at us like this. So still in the xy plane, but yeah, at that angle. So we're going to try to figure out what kind of path this one would take. So first thing to do is step 0. We've got to find components. So I found the components, the way I did it, I found the y component, or the j hat component. Yeah, j hat and I hat are back. I did j, meaning y, and then I, meaning x, in that order, because that's the order we're going to handle what's going on. So anyhow, yeah, a little bit of trig. So to get if it's coming in like this at this angle, this component would be the opposite. So that must mean sine. So you figure this out. And hey, you get that velocity again, 2.25 times 10 to the 7th meters per second. And then to figure out the component along the x-axis, it would be that initial velocity times the cosine, so you get this number again. So these are our two velocities. So this guy's going to come in like this. If we look first at the force that's caused by the y component of the velocity. So this is the one going to the right is the y component. This one's the dark purple one. So this component here, this component here. Remember, we figured out using our right-hand rule and flipping it that this force is going to be up. So yeah, we have this number of force again, and that force is going to cause this guy to move in a circular path. So yeah, when it's moving this way to the right, the force is straight up. As it starts to curve around here, the force is going to keep going that way, perpendicular towards it. So it's a centripetal force. So that force will cause this electron to move in a circular path in the YZ plane. So look back up here, see Y, see Z, and think of this plane, and know that this force is going to cause this guy to go around and around like this. So that's that one. When we do the same thing for the X component, so the component that's coming towards us out of the page, you plug in the things. This is our V sub x. This is the X component of the velocity. So you plug all that in, QVB sine theta, but theta again in this case is 0 because the angle between the X component of the velocity and the magnetic field, well, they're both coming straight out of the page, so the angle between them is 0. So that's 0, which means the X component of the velocity is not going to cause any force on this electron. Therefore, the X component of the velocity is not going to change because this electron is just going to keep moving with the same X velocity the whole time because of Newton's first law. If an object is in motion, it will stay in motion in a straight line unless acted upon by an outside unbalanced force. So yeah, nothing will change the X component of this velocity. So what do you get when you combine these two things? So we've got the Y component of the velocity, the part of the velocity that's always perpendicular to the direction of the magnetic field, causing this guy to move in a circular path, whereas you also have the X component of the velocity, which just causes this guy to go in a straight line path. So pause for a second. Think about what that would look like, because I think it's fairly interesting. It would cause a helix. So as this electron is coming from back here this way, all of a sudden it enters this magnetic field. Part of its velocity is going to make it go in a circle, but while it's going in a circle, I should be drawing it this way or on this drawing, but while it's going in a circle, it keeps moving in the X direction, and that motion is unchanged. So you end up with this neat helix thing. So pretty neat. So to review, let's review quickly. I feel like this video is getting long. So what was the first right-hand rule we learned in the first part? The first right-hand rule is Ampere's grip rule. Grab the wire with your right hand, point your thumb up, put your thumb in the direction of the wire and of positive current, and the magnetic field will go around in the direction your fingers go around. The second right-hand rule is the cross product rule. So your thumb is always the direction of the motion of positive charge or positive current. Your fingers are always the magnetic field. And if you're doing this rule, your palm is pointing in the direction of the force that this charge will feel because of the magnetic field. So how do you deal with negative charges and currents? Well, it's kind of up to you. You can either do right-hand rules and then flip it when you're dealing with a negative charge or a negative current, or you can use the left-hand rule. Up to you. You should get the same answer. Oh, I should have changed this part. Yeah, that shouldn't be. This should be an I and an arrow. This should be a negative I and an arrow pointing down. Is what that should be. Oh well. Too late. Not changing it. Same deal here. Notice your right hand and your left hand. Yeah, they're kind of mirror opposites. You'll be doing a lot of holding your hands in front of your face and trying to bend your wrists in unusual positions in this chapter. It's weird. You'll get used to it. So what is the formula we learned today for the force on a moving charge in a magnetic field? It looks kind of like the other formula we learned in the previous part of the slides. F is equal to QVB sine theta, where theta is the angle from V to B. And finally, what step do you have to do when your charge enters your magnetic field at some angle other than 0 degrees or 90 degrees? If it's just 0 or 90, you can just do a right-hand rule or a left-hand rule and figure it out pretty quickly. But if it's not one of those, you've got to do a step 0. You've got to find the components of this and then apply your right-hand rule to each of the components. Well, really just to this one. This is the one that's perpendicular. If your velocity is parallel to the magnetic field, there isn't going to be a force in it. So that's it for this part. Hopefully you found that interesting.